Hey guys, welcome to lecture 9 of the RISC-V processor design course. Today we're gonna focus on memory access, load, stores, how can we improve the performance, to what extent, and how we move forward. So let's get into it. So the first thing we need to define is our data closely coupled memory, the DCCM. And this is something that we spoke about a little bit in our previous lectures, but this thing is similar to the ICCM. It's a 4 kilobyte 32-bit words times 1024 rows. It's byte addressable. It has one read port and one write port, one clock cycle latency for loads, and has in order responses as you would expect by an SRAM. In terms of where this DCCM sits, it sits on the core top here inside all the other things. We could have put it outside. It really doesn't matter where we put it. As of now, we're gonna see maybe in the FPGA lectures that we're gonna pull it outside because we want to synthesize the core and then synthesize the memories aside, but for now we just put it in here along with the ICCM. So that's where the DCCM memory lives, and let's start talking about loads. And loads is the technical operation of moving data from the data memory, from the DCCM, inside the register file of our processor. So it's extremely simple in principle. We have different kind of loads. We have 5 types of loads in RB32I, and those are load word, load half word, it can be signed and unsigned, and load byte, it can be signed and unsigned. And this has to do with how we fill up the upper part of the register when we load something that is less than 32-bit. So in terms of loads, we can distinguish between 2 kind of loads, and the main 2 categories that we're gonna focus on are aligned and unaligned loads. We saw that the DCCM is going to be aligned to 4 bytes, so 32-bit, because each row is a 32-bit 4-byte row. For unaligned loads, it means that we need to load 2 rows. 2 reads, it means they're slower. So let's start by analyzing which loads are aligned. So byte loads are always aligned. Since the memory is byte addressable, we only need to load 1 row to get that byte. Maybe we have to shift right to get that byte, but in terms of how many read requests we have to perform to DCCM, it's only 1, always. When we're loading 16 bits, so half words, those half words are aligned whenever the address is even. And words are aligned, word loads are aligned whenever the address is a multiple of 4. And let's see here, what do we mean? So if the address is not a multiple of load, so here we have x0 plus 2, so we're reading from address 2, it means that this is address 0, this is address 1, address 2 starts here. It means that if we want to read 4 bytes from address 2, which is here, we need to read byte 2, byte 3, but you see byte 4 and byte 5 that we need fall onto the other row. So we need to perform 2 read operations, have a load buffer, and then combine the result back together to get this value, which is B2, B3, B4, and B5. When we are loading ALF words, we are looking at, in particular, if we are accessing this column, so the column of 3, 7, B, and F. If we're accessing this column, if this is the base address, it means that it's going to be unaligned. Because if we want to load an ALF word here from address 3, what's going to happen is that we're going to need also byte 4 that lives on the other row. So this requires loading the second row. So how can we build a load and store unit for the current DCCM architecture? Basically, one thing that needs to happen is that we need to arbitrate access to the only read port. We just have one read address active at each given time. So it means that whenever we have an unaligned load, we need to stall the pipeline, read the first row in the DC1 stage, read the second row in DC2 stage, combine the results in DC3 stage, and send to write back. Let's take a look at the RTL real quick. So the LSU unit lives in the EXU unit, and the LSU unit is a fully pipelined architecture. There are 1,000 different ways you can do, especially when the memory architecture starts to get complicated. But this is a fully pipelined architecture. We have a DC1 stage, DC2 stage, DC3 stage that leads to the write back. So let's start looking at what happens with loads. Okay, whenever we have an LSU operation, the first stage is to flop whatever we're sending down the pipe. So the second operation after the DC1 stage, what we do is we basically try to understand what kind of operation we have. We calculate the address where we're going to do the load or the store, since the address is calculated the same way. And we try to understand if we are dealing with an unaligned address. Okay, so if we have a word, if we don't have a multiple of 4 address, so if any of the lower 2 bits are 1, it means that it's not going to be aligned. And if we have, again, the third, like the last row, as I said, we AND together the first 2 bits, and if this is 1, it means, and we are loading an ALF word, it means that that's going to be an unaligned access. So with this information, we go down to DC2 and we basically load the data here by putting those address out. So here we have a load, a valid operation. It is not an unaligned address, and we go to the computed address. Okay, then to make sure that we deal with unaligned address properly, I need to add a little bit of extra logic here whenever we stall the pipeline to deal with unaligned addresses. After that, we go to the DC2 stage. We try to understand if we need to load another row because the load was unaligned, and this is where we have here the and with the DC2 unaligned address. And as you can see here, we put out the original address plus 1. So here we are fetching the rows. We're fetching the first row and the next row to create the picture. And you can see here we create a load buffer, and we will arrive to this forward value in a minute. But we're basically getting the data from the memory, shifting it properly with the computed address, the lower bits that identify the byte in the word. Then we go to the DC3 stage. We do the same thing if we had to deal with an unaligned address here. And then we go straight to write back here. Okay? And we, of course, we mask the data, because if we're loading a byte, we just want a byte. If we're loading an ALF word, we are just loading an ALF word to the register file, and the same thing for the word. So all those masks make sure that we are we are committing data to the microarchitectural state. We're committing only the data that we need. So this is pretty much how the loads work for aligned and unaligned cases. And you have a small test case for both stores and loads that you can run now it's part of our smoke test suite, and we can take a look at the basic load test. And here we are basically testing all the different kind of loads, aligned, unaligned, and all the stuff that we need to make sure that the pipeline is working properly. Also the stall logic, as you can see here, we are sending 3 unaligned loads one by one. We are making sure that the stall logic is working, spacing those loads by 1 clock cycle. Otherwise, we are not gonna be able to use one read port. In fact, if you can see here from a performance perspective, if we look at the RTL log of the loads, you can see here that the first load is aligned. The second load gets scheduled right after it. So we are at cycle 7, cycle 8, but then these loads complete in 2 clock cycles. So from 8 we pass to 10, 12, 14, 15, 16, 17, because we have all byte loads. So those are always aligned. Then we have alpha word, alpha word. Okay. And then we retire. So this is aligned, this is aligned, this is aligned, this is unaligned. But we don't see it here because we don't have the cycle count of the next instruction. So this is how the basic load test works, and makes sure to analyze all those corner cases of stalling the pipeline and whatnot. Now, how can we improve the performance of unaligned loads? Because you can see right now it takes 2 clock cycles to load data from an unaligned address, and there's really nothing you can do. You're limited by the bandwidth of the memory. You're limited by the fact that you only have one read port. And so there's no other solution than to get a DCCM with an extra read port. So you have an extra read address that you can use. You fetch two rows at a time. So from great powers derive great responsibility, meaning that now what you can do is you can issue 2 read operations in parallel if you have aligned accesses. You can do a lot of things whenever you have more resources, but of course it's going to be expensive from a reordering logic to make the most out of that infrastructure. So this is something that we're going to see in more advanced courses. I put a link below here for you to check out all the courses that I offer. I'm going to roll out 5 or 6 different courses over the next month, so make sure to check those out. Now, we dealt with loads. Now we have to deal with the concept of stores, and everything that we talked about regarding alignment is still important, but the other important thing is that, are we writing the entire row? Because if we're not, we need to read the data, update it, and write it back. And really the only case where we do not need to read the row first is when we are writing the entire row, whenever we are storing an aligned word. First read, update inside a store buffer, and then commit back the data. So we can see it here, how it goes. Let's take a look at the LSU. So here I have a signal that says that the store needs loading. And the store needs loading whenever we have a store and we have a byte, an half word, and a word store that is unaligned. Okay, because whenever we're writing a byte, the other 3 bytes don't change, right? So we load the previous word, we swap that byte inside our store buffer that we're gonna see, and then we write back the entire row, update it down. So here you have the store buffer, and this is where we take the data from that we read from the address, and we mask it out with the mask that we created here, and we inject the new data, again, the data that we have masked it out. So this is the nice thing about everything that we are doing here. So everything goes, it's all ends and ors, updates. It's extremely tight in terms of logic. And the same thing we do if we have an unaligned store, we need to do the same thing for the next row. The nice thing here is that we can reuse most of the logic that we had for the load operation. Okay, and so here the store buffer comes into play, and basically we do the same thing for the next row. As you can see, we still have one read address, so we have to make sure that whenever we have an unaligned store or an unaligned store followed by an unaligned load, we are stalling the pipeline to make sure that we are properly using this one single resource that we have. Now, if we take a look at how can we improve the performance of this thing, because remember, if I need to load every time I store, and I have a sequence of stores, and I'm doing something like pointer chasing, or I am storing bytes, 1 byte at a time, I need to wait for the previous stores to complete before I can perform my store. How can I improve this is to have forwarding paths inside the LSU, and this is called store forwarding. And basically, if we are writing to an address that is being read either by a load or another store that needs to load, we can forward the data. And this is a very powerful optimization. It's extremely important whenever we are doing heavy memory operations, especially if we are doing AI accelerators and AI processing. But of course, this is important also for general purpose computing, and memory loads are the bottleneck of our system. The processor can work so much faster than the memory. How do we avoid loads when storing? This is a more complex topic, and again, this falls back to the memory architecture and bus that we are using. And we typically get rid of the loads on writes by using byte enables, and more complex bus architectures like the AXI bus, AHB bus are designed for this and much more. For example, they support out of order loads and stores and all these complex things, especially when dealing with dynamic memory. This is also something that I cover in my advanced course, so if you're interested, make sure to check that link out. So let's take a look at this store tab. So first thing that you notice is that in the previous task we had a memory initialization file, so basicload.mem. Here in the store we don't have a memory initialization file, so I manually initialized the rows that I needed to 0. Okay, and you can see here, and I'm showing you this. This is a 4-state simulator. Again, this is something that we use in my more advanced courses, but I wanted to show you here because those axes are not visible on Verilator. But you can see here that when we are not initializing the memory is giving us garbage with all axes, but then once we initialize with the first slew of writes here, you can see that we are triggering the write data. The memory starts to give us back zeros or all the data that we want. And here, this is the LSU in all its splendor working, and you can see that we are correctly scheduling all the instructions that we need, and you can see here that we stole just the ones. So this is a pretty nice thing, meaning that we are not stalling the pipeline unless we really need. This is so important for performance. We can get better than this with the current memory architecture and the current bus architecture. Okay. So I strongly encourage you to dive deep into the test that you have here. So this basic store test and maybe comment out the different sections of this test and execute it one by one and make sure that it's adding up in your mind whatever is happening in the memory bus, both the read and the write port. This is the overview of how the load and store unit works in this TinyVetus processor. We have just one thing left before wrapping up this course, which is how to handle branches. And branches are basically whenever a program takes an if, an else statement, a go to, a while. So how do we map those high level constructs to these branches, so jumps in the program, and how those jumps are performed inside TinyVetus? We will see that we need to implement a pipeline flush logic. We're going to see that we are going to adopt a policy-based branch predictor, and this is pretty much what's left before running a full benchmark and see that everything is working nicely. So I hope you are enjoying the lecture so far. I know we are covering a lot of concepts, and I know that this thing is going to require a lot of time from you to fully understand, but it is better to understand it this way than read it from a textbook. At least this is my opinion. So I'll catch you on the next lecture.